So it's not my intention to be so severe, for not saying in other words, for asking you some very long thesis on some very hard topic. The idea that I had in mind for the report was the analysis, for example, of a problem like the birth rate. Of course, not half a page like I've done, probably 5-6 pages, well, as much as you can write of these things, possibly with some analysis with computer system, but this is the kind of problem. Okay, so a colleague of yours, Michael, for example, was proposing a very difficult thing. So I was, oh, well, yeah, okay, if you want to do that, happy to see that you want to do that, eventually, even if it's already almost ready. But the point is that this is not a thesis, so take it easy, guys, okay? So we were introduced the Voltaire equation with this example of the birth rate. And then we have seen that the Voltaire equation can be used to reduce initial value problems for ODEs. Well, we have seen this for first order initial value problems and second order initial value problems, which can be reduced to Voltaire equations. Voltaire integral equation. What I would like to do today are the following things. First of all, prove the reverse, which is possible to transform a Voltaire equation into an initial value problem. Second, give a possible way out for finding the solution of a Voltaire integral equation. Then I would move to the Fredholm equations, which I want to touch only for some peculiar case, for some special case. And then what is more important today is green function. So I would like to explain Green's function. Have you ever heard about Green's function? No, cioè Green credo che sia lo stesso Green, sì, però questa è la funzione di Green. It's the Green's function that allows you to solve ma dai, ma che schifo, ma c'è i professori ci mettono le gomme da masticare sotto. Yeah, the Green's function is a method that allows you to solve boundary value problems. No, okay. Okay, this is the menu, this is the idea. Let's see how much of this we can do. So let's start by completing our discussion on the Voltaire equation. So we will start by seeing how is it possible to start from Voltaire and recover an initial value problem. Initial value problem. In order to do this, let me introduce a formula which I do not intend to prove because it's something very boring and very, not very long, but it's very boring, which is the Leibniz integral rule. I would ask you to accept as a matter of fate, that this rule is true. If you want to check it, you can check it. If you want to do the calculation, you can find on Wikipedia the calculation, because I've seen that there is a Wikipedia the calculation. It's a very long page. Read the Wikipedia page and convince yourself that this formula is true. So the Leibniz rule allows you to find the derivative with respect to x of the integral of some function f of x and y in the y when the extreme of integration are themselves functions of x. If the extreme of integration are not function of x and the mod of the fact that the f and its derivatives are continuous and integrable and blah blah blah, you could move the derivative with respect to x inside the integral. But since the extreme of the integral are functions of x, you cannot do that. What you can prove is that this thing here is equal to the integral between a of x and b of x of the partial derivative of f with respect to x evaluated in x and y, the y, evaluated, well, function of x and y, the y. You understand this this notation, no? This is this object here. Okay? Then I have plus f evaluated in x b of x times b prime of x. This b prime of x, I like it because I'm using that's right in this way. And then I have minus fx a of x derivative of a of x with respect to x. Okay, so this is what is called the Leibniz integral. Here. It's disappeared. What's disappeared again? Oh, yeah. Yeah, there was just something that disappeared. Yes, I know. And this is the derivative of f with respect to x. Almost impossible. Okay, we need to use this. If we use the Leibniz integral rule, well, the proof that you can write a Voltaire equation in an initial value problem is absolutely straightforward. It's just an application of this rule. For example, let me consider the following Voltaire equation, which is the one that we found yesterday for when we transform for the first order initial value problem to the Voltaire equation. Was this equation here? Go back in your notes and see that was this this equation. This is the Voltaire style equation. Probably here it's an S, not a T. Okay, so what shall I do now? I can take the derivative with respect to S on the left hand side and on the right hand side. So derivative with respect to S, I think right in this way to be quicker. So the left hand side derivative with respect to S of U of S is well, let me call U prime of S. Is the derivative to S of U. The derivative with respect to S of U0 What's the derivative with respect to s of u0? 0. And then what I have is the derivative with respect to s of the integral between t0 and s of ft u dt in dt. So I have to evaluate this integral using the Leibniz Rule. So this thing is the this is correct. This is correct. So this thing is gonna be the integral of between t0 and s of the derivative with respect to s of f t u dt in dt plus sorry, this is a partial derivative plus this term here. So it's f evaluated in the upper extreme. So this is gonna give me f of s u s times the derivative of the upper extreme with respect to s. So times the derivative of this thing s with respect to s, which is 1. Then I have minus f evaluated in the lower part on t naught, f of t naught u t naught times the derivative of t naught with respect to s. This thing here does not depend on s. It's a function of t and u of t. So this thing is 0. T naught is not a function of x. So the derivative of t naught with respect to s is equal to 0. This term is also 0. This object here is the s in the s, it's 1. So how can we rewrite then this equation? Is u prime of s is equal to f s u of s. In the particular case in which I'm I'm taking into account again the Voltaire equation without taking the derivative yet. And I consider the extreme which makes the integral vanishing. So basically, I'm taking s to be equal to t naught. No? If I'm taking this thing, this means that I'm evaluating u in t naught. Taking the Voltaire equation. In the Voltaire equation, what happens if I calculate u of t naught? U of t naught is u of naught, u0, plus the integral between t0 and t0 of this thing. But the integral between t0 and t0 is 0. So u of t naught is equal to u0. This allows me to say that the Voltaire equation, this Voltaire style equation which is written here, is equivalent to the initial value problem where you have this first order differential equation and where I have these initial value conditions. And if you go back in your notebook, you will see that this is exactly the problem from which we started yesterday, that we proved to be equivalent to Voltaire integral equation. Problem, the initial value problem first order that we proved to be equivalent to Voltaire integral equation. Now, the big problem is, okay, that's fine, but you are saying all these things about the Voltaire equation, we haven't seen yet a solution. That's true. So, the idea now is trying to reconstruct a solution for the Voltaire equation. Why? So, we have proved that you can basically jump as you want from initial value problems, at least first and second order, to Voltaire equations as you like. Why we have done this? We have done this because sometimes it's easier to solve the initial value problem, other times it's better to solve the problem in the formulation of the Voltaire equation. So, how do you solve the Voltaire equation? What you use is what's called the Picard method, which is basically generating approximate solutions of the exact solution of your problem. So, in the linear case that we have seen now, we can we can write the solution U as U of t equal to some f of t plus lambda integral between a and t k of t s u s. You remember, this is actually the general form of the Voltaire equation that we were showing before, yesterday, sorry, where this k is the kernel of the equation. And if you remember, we said also that we can use this notation that you don't like, the operator equation. So I can write this as f plus lambda capital K u. And I already told you that when I'm using this operator equation, is basically it's easier if you think about this as if I'm writing some matrix equation. Okay. So basically, this lambda ku is just a short notation for what I wrote here. It's lambda times the integral between a and t, etc., etc. So if I move the part in u on the left-hand side, what I get is some u. Sorry, what I get is I can put it here this way. Identity minus lambda kappa applied on u equal to f. Why? Probably it's better if we're doing all the passages here. So let me move this thing on the left-hand side. What I get is u minus lambda kappa u equal to f. You remember, think like if these were matrices. So if these were matrices, what you would write is in reality this thing here. Well, this object is the identity matrix. In this case, is the identity operator. But remember again the parallelism with matrices. So I can put outside u. I cannot put outside in front. It should be on the right because these operators are acting on the left. So this is identity minus lambda operator k u equal to f.
So you're doing this in order to
find the solution for you for the Voltaire equation. So this is in some general way to write a first order, a linear Voltaire equation. I want to find the solution to this equation, or well, at least a method for finding the solution to this equation. So now let me move this operator on the right hand side, just the operator. How I'm doing this? Again, imagine this is a matrix. So if this is a matrix, in order to remove this, what I have to do is to multiply by the inverse of the matrix. So what I'm doing here is multiply by the inverse of the operator. On the left. So the inverse of an operator times the operator is like the inverse of a matrix times a matrix. It's the identity. So this object here is an identity. Then what I get is identity times u equal to 1 identity minus lambda kappa minus 1, this minus 1 is the inverse of the operator, times, applied to the function f. Now this object here is trivially just u. So this tells me that the solution to the linear Voltaire equation can be written as the inverse of this operator applied to the function f. Now what you do is to so the inverse of this operator is just a formal expression that you can rewrite using Taylor expansion. Okay, so basically what you can say is that this operator here is in reality the Taylor expansion with respect to this operator, and you can rewrite this. How do you write this thing if x is a small parameter? This would be something like 1 plus x squared plus x cubed, etc. In this case, that's exactly the same. So you write this operator here as identity plus lambda kappa plus lambda squared kappa squared plus higher order operators. And this thing acts on the function f. Now what you can prove is that this series, this sequence converges to the exact solution of the integral equation. So what does this mean? What does this sequence mean? So basically what you are doing is apply the identity to f. What's identity times f? F. And this is easy. Now, add lambda kappa f. What's this thing? Remember the definition of the operator kappa, okay? Delta, integral of k of what?
Yes.
Ts, yeah, I don't know. Let's say Ts, yes?
Fs
Fs, the S. That's fine. With the lambda in front, where's the eigen? Okay, with this thing here. Then I have lambda squared k squared f. What's this? Lambda squared. This is some integral between a and t of k t s of the integral between a and s of k t how can I call it q f q the q the S. Do you see the logic? No. Do you see the logic? Can you understand the logic? So basically what I'm doing here is kappa of kappa f. So I've done kappa f, which is this thing here. Well, of course, I cannot use t because then I'm doing another integral outside t. And then I do kappa of kappa f. So, and I got this this expression, large expression. And that's the same for all the other powers, as many powers as you want. All right, so suppose that I'm given the let's call the initial condition, the initial value condition. So suppose that I have some, I've been assigned the u of t naught, which I call u0. Then what I can do is to write the sequence of u's which are approximating the exact solution. So what I will have is that the term of the sequence n plus 1 will be f plus lambda k u n. Un will be, I can write this as f plus lambda k times un. What is un? Is f plus lambda k u n minus 1, and so forth and so on. So this means that if I know u0, I can reconstruct all the u's of my sequence.
Those are capital K operators.
These capital K operators are, these capital K's are all the operators, so integral between a and t of the kernel, k of x and y, times the function on which they are operating. Of course, when you have, typically when you have a problem, so this is the general theory. When you have a practical problem, in principle, you should have assigned the kernel of the problem. So you know what's kappa. You know what's k, put it this way, the kernel of the equation. So you know what's the operator kappa. And in principle, you know f. In principle, you know the initial value of the function. So you know u0, u0, and you can reconstruct all this sequence. And you know that theory tells you that this sequence converge to the exact solution of the equation. Okay. Actually, you can rewrite this in another way. You can write this as f plus the sum from 1 to n of lambda j kappa j applied to f. Because anytime that you are adding, that you are developing these terms, you will get lambda kappa f. Lambda kappa f, lambda kappa f until the end. So if you are doing this procedure until the end, what you will get is an expression like this one.
Just a slide for a moment, right, this.
Yeah. From home, any problem, any question? Posso tornare a sinistra? No. Okay. Then we will start a new section. And we'll talk about the Fredholm equation. So if you remember, we have defined the Fredholm equation when we've defined the general integral equations as that equation that can be written in this way: the integral within a and b of k x y u y d y minus lambda u of x equal to f of x. Salute. So basically the difference with the Voltaire equations, we say that was in the fact that this extreme was, this limit of integration was, is a constant for the Fredholm equation, while instead is a function for the case of, well, it's x, for the case of Voltaire equation. So I'm interested not to I'm not going to discuss the most general form of the Fredholm equation. Instead, what I'm interested in are those equations for which the kernel can be rewritten as a sum of products of function of x and y, a finite sum. So I want to write the kernel as the sum, a finite sum, so between 1 and n, of products of functions of x and y. So I'm interested in problems where I can write the kernel in this way. Kernel of these ones is called separable. So if I have something like Separable. Yeah, I'm thinking some kind of counterexample. If I have something, for example, like this one, this would not be separable because I cannot write this as a product of a finite product, a finite sum of products of function of x and y. Okay, if I have something instead like x plus x squared y, for example, this is a sum of x, which is basically would correspond to a1 of x equal to x, beta 1 of y equal to 1, and then I have alpha 2 of x equal to x squared, and beta 2 of y equal to y. So in this case, I can separate. So I would have a separable kernel. In this case, I cannot separate because I cannot do this this kind of I cannot write this thing in this way. Okay, this means that if I'm considering this separable kernel, I can write the Fredholm equation as the integral between a and b of the sum from j that goes from 1 to n of alpha jx beta jy times uy in the y, and then I have minus lambda ux equal to the function f of x. Now, last week, yes, we introduced the inner product. What's this object? Can you write the inner product between u and bj in the interval from in the interval ab? How would you write this? Sorry, not beta j. Don't look at the notes. Vabbè, you can look at the notes. How would you write this?
Integral between a and b of uj of x.
What?
U of x.
U of x.
Of x and beta of x. Yeah.
Beta j x in the x. That's correct. This is an integral. This is going to be a number. So let me call this number Cj. Then, how can I rewrite this object that I have here? The first term of the Fredholm equation. So I can rewrite this term here as I can put the sum outside the integral. And also the alpha j of x, because these are function of x and I'm integrating in the y. And then what I have is the integral between a and b of beta j of y, u of y in the y. What is this? It's exactly this object here. This one. So this thing can be rewritten, can be simplified even more, and written as the sum for j that is going from 1 to n of alpha j of x times the coefficient that we have called c of j. So let me complete the equation. So here there is a minus lambda u of x equal to f of x missing, and there is minus lambda u of x equal to f of x also here. Now what I want to do is to take again, to multiply, to scalar multiply, to take the inner product of the entire expression with beta, with the function beta i's. So what I'm doing is this and this. It's like when I'm taking, imagine that I'm taking the derivative on the left and on the right, or I'm taking the integral on the left and on the right. Here, what I'm doing is to do the inner product with beta I on the left and on the right. So, what does this mean? This means that let me take the right because it's easier. If I'm taking the right, this is going to be the integral between a and b of beta I of x, f of x in the x. That's the expression of the inner product. Why am I doing this? Because these are numbers. Wow. These are numbers that I want to call f, capital F of I. These are actually n numbers because this I is the index of beta I, and I have n betas. You remember, the sum goes from 1 to n. So I have n different betas. È chiaro? Verità? Let's see on the left hand side. On the left hand side, you should recall the properties of the inner product, which are the same properties of the scalar product. So among them, there is linearity. This means that the left hand side can be written in this way. It's the sum between 1 and n of the inner products of beta I, alpha j, c, j minus lambda inner product between beta I and u. Guys for home, is this clear, or should I explain how did I find the left hand side? Oh.
Sorry, can you repeat?
Yeah. Is it clear how do I arrive to this expression here from this one?
No, Professor. Could you please explain it?
Okay. So we have said a couple of lectures ago that the inner product is linear. So if I have the inner product of u with v plus w, this would be equal to the inner product of u with v plus the inner product of u with w. That's actually what I'm doing here in this case. So what I'm doing in this case is I have the inner product of beta I with this object here. So I can write this as the inner product of the sum alpha j cj minus the inner product of beta with lambda u. Now, lambda is a constant, so another property of the inner product tells me that this guy here is equal to minus lambda times the inner product of beta with u, beta I. What about these other things? Here I have to use linearity again. This expression here is basically the inner product of beta I with what? Alpha 1 C1 plus alpha 2 C2 plus other terms until I arrive alpha n Cn. So if I use again linearity, I can write this object as the inner product of beta I alpha 1 C1 plus beta I alpha 2 C2 plus blah 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 beta I alpha n Cn. And then I have minus lambda beta I. So these terms here then can be written with C1 are numbers, Ci's. So C1 is a number, C2 is a number, C3 is a number, until Cn, which are numbers. So can be taken outside the inner product. And this would become the inner product C1 times the inner product of beta I with alpha 1 plus C2 inner product of beta I alpha 2 plus blah 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 until I arrive to the last term. And then I have minus lambda beta I u. Now, this sum here can be rewritten as the sum over j that goes from 1 to n, which is here, of Cj inner product of beta I alpha j. And then I have minus lambda inner product between beta I and u. And this is what we have written here.
Yes, Professor, I got it. Thank you.
Okay. Now, this inner product between beta I and alpha j, these are numbers. This can be written as alpha ij. These are, sorry, capital A ij. These are entries, can be seen as the entries of a matrix capital A. These are numbers because these are basically the integral between A and B of beta x, alpha jx in the x. So these are numbers. The only thing I will add an I and j, some indices to consider all the possible combinations. So this means that I can rewrite my expression. Right. What are the beta I u? What are the inner products between beta I and u? This is what we have defined before. These are exactly Ci. Because we have defined the inner products between u and any function beta as this element Ci. So I can rewrite the equation as sum over j going from 1 to n of capital A, I, J, C, J minus lambda C, I equal to what we call the Fi, capital Fi. What's the point of this thing? The point is that now I can write this equation in matrix notation. This is now true matrix. This is matrix A minus lambda times the identity matrix that multiply in the matrix sense, so row by column, the vector C equal to the vector F, where C is the vector which is given by C1, C2, C3, etc. And F, capital F, is the vector whose components are F1, F2, F3, blah blah blah, Fn. Actually, these are columns. Let's see. Now this is a system. What's the problem? Non ho capito.
Se c'erano disponibili sulla...
Sta roba qui? No, questo è trasposto.
Ah.
È per dire che queste non sono righe ma sono colonne. Cioè l'ho scritte come righe, però per funzionare devono essere colonne, altrimenti non posso fare il prodotto riga per colonna.
L'identità è matrice identità in questo caso. L'identità è la matrice identità.
In questo caso è la matrice identità. Sì, questi sono, adesso questo è proprio matrix. Matrix equation. It's a real matrix equation. Okay. Not real, in the sense it's a true matrix equation. So, why bothering with this? We are bothering with this because basically now, what is this? This is the matrix form of a system of algebraic equations. So where your incognite are the CIs, the numbered CIs. So basically what you can do, this is an algebraic system. What you can do is take in this system and use trivial algebra to find the coefficients CIs. If you find the coefficients CIs, then you have solved your problems. Why? Because let me go back very quickly to no. It was this one. So let me go back to the form of the Fredholm equation with this separable kernel. We have written this as the sum the sum for j that goes from 1 to n of alpha j x cj minus lambda u of x equal to f of x. If I'm solving with respect to u, what I found is u of x is equal to, let me change the sign here. So there is a minus here, a plus here, and a minus here. So I can write this as u of x equal to 1 over lambda that multiplies minus f of x plus the sum over j of alpha j of x c of j. The alpha j of x is something that I know because actually it's the kernel, is given by the kernel of the problem. So this tells me that if I'm able to find cj, then I'm able to find the solution of the problem. Because if I have cj, f of x is given, alpha j is given, lambda also, well, lambda is a kind of, we have to discuss about lambda, then I'm able to write the solution u of x of the Fredholm equation. So the idea is that I should be able to find this c of j. C of j, I can find the c of j if I'm able to solve this linear system. And again, this is a problem, an algebraic problem. Now we can say something more. C'è un eclisse, non si vede niente oggi. Vedo senza. So we can say something more, which is the following. Actually, we know that there are some methods to study the solution of this system. The idea is that you have to involve the fact that you have to calculate the determinant of this matrix here. Now, if the determinant of this matrix is different from 0, do you remember? No, you don't remember. What's the solution? You don't remember. So, if you have a system like Ax equal to this thing here, okay, where the incognita are this x, okay, in order to find the solution of this system, what you have to do, but in order to know if there is or not a solution of the system, what you have to do is to study, to see the determinant of the matrix which is in front of x, the determinant of A. If the determinant of capital A is different from 0, then you know for sure that there is a unique solution. So if the determinant, using the same B, I do not want to confuse with this one. This is some matrix. So if the determinant of this object here is different from 0, there is a unique solution. So if I'm going back to the matrix form of this equation that I've written here, this means that if the determinant of this matrix A minus lambda identity, if this determinant is different from 0, then I know that there is a unique solution. Actually, this is something that should look to should sound familiar to you. What is this object? Wow, yes. So basically, this is when you want to find the eigenvalues of a matrix. That's exactly the kind of equation that you want to solve. So the eigenvalues of the matrix A are those lambdas for which the determinant of A minus lambda identity is equal to 0. So this basically means, since you do not want you want this to be different from 0, this means that if lambda is not an eigenvalue of the matrix A, which I remind you, the matrix A is the matrix that you obtain from the inner products of beta I and alpha j. So, yeah, if lambda is not an eigenvalue of this matrix capital A, then this means that this determinant is different from 0. If the determinant is different from 0, then this equation has a unique solution. It means that you have a unique solution of these numbers Ci's. On the reverse, if lambda is an eigenvalue, of A, which basically means that the determinant of A minus lambda times the identity is equal to 0, then either you have no solutions or you have infinitely many solutions. Infinitely many solutions, infinite solutions. And this depends on the vector f. So then what you have to do is to study the vector f. So you have to study the augmented matrix that include also the vector f to establish if there is no solution or if there is an infinitely many solution. Now, there is a special case for lambda equal to 0, but I do not want to bother you. You can find directly in the notes the special case for lambda equal to 0. But in any case, lambda equal to 0 is a special case. See notes. Guys, if you allow me to do an example, then we can have our break. But I want to do the example before. So what's the example? The example, let me consider the operator k, which when acting on the function u, gives me the integral between 0 and 1 of 1 minus 3xy times u of y in the y.
1 minus
3 Cioè, sta lì che non sai vedere questo
No, trovo un beta senza ridere.
Vabbè.
È strano vedere i numeri.
So let's see what's the kernel. The kernel is then this object here, right? This is our k of x and y. Now, so this is k on x and y. Is this separable? Yes, it's separable. So separate for me this this kernel. How would you separate this?
Alpha 1, beta 1, equal to 1.
Alpha 1 and beta 1 equal to 1. Alpha 2?
Equal to x.
Alpha 2 equal to x.
And beta 2 equal to 1.
And there is a 3.
Either in alpha 2 or
Yeah, that's fine. I put in alpha 2 because I put like in alpha 2 because that's where I have in my notes. So basically this is separated in this way. Now let's construct the matrix A, capital A I J. So you mind this is equal to the inner product of alpha I with beta j. So in this case, the integral is between 0 and 1. How do I know? Because that's actually the boundaries of my problem. So the integral is between 0 and 1 of alpha I of x, beta j of x in the x. Oops, the x. The fact that I'm writing here beta in y does not mean that I have to write this always as a function of y. This is a function. This is a function of something. But this something can be mu. Indeed, what I have to do is to write this thing as this one when I'm performing these integrals. That's like, imagine that I'm saying, evaluate this function. This is equivalent to say, evaluate beta j when y is equal to x. That's the same. So let's evaluate this thing. I will have a11. Who is a11? Is the integral between 0 and 1 of alpha 1, which is 1, times beta 1, which is 1, in the x. So this is the integral between 0 and 1 of 1 in the x. And this is x between 0 and 1, which is 1. What's a12? A12 integral between 0 and 1 of alpha 1, which is 1, times beta 2, which is, in this case, x, in the x. So it's the integral between 0 and 1 of x in the x. Prima riga, seconda colonna, me l'ho messo tutto sopra. Yeah, there is a mistake on my notes. Well, in any case, I will change it later. Then I have a21, which is the integral between 0 and 1 of alpha 2 minus 3x times beta 1, which is 1 in the x. And this is minus 3x squared over 2 between 0 and 1, which gives minus 3 over 2. And finally, vabbè, questo qua avevamo detto nemmeno 3 mezzi. And finally, there is the A2, and no. Integral between 0 and 1 of minus 3x times x in the x, which is minus 3x cubed divided by 3 evaluated between 0 and 1, which is minus 1. Come on. Guys, from home, any problem? Until now.
I'm sorry, Professor. A12 that you wrote 1.x. I can't understand what you wrote x.
That's actually what I was saying before. So basically, the definition of the Aij is the inner product between the alpha I and the beta j, which basically means it's the integral, in this case between 0 and 1, of alpha I of x times beta j of x, again x. So basically this is equivalent of considering beta j of y when y is equal to x. Okay? This means that since here I have a beta 2, this is beta 2 when y is equal to x. It is this object, which is x. Okay?
Yes, Professor. Thank you.
Okay. Then we get this matrix here. What do we do with this matrix? Let's find the eigenvalues of the matrix. The eigenvalues of the matrix are given by the determinant of the matrix minus lambda times the identity matrix equal to 0. So we have to solve determinant of A, which is 1/2 minus 3 over 2 minus 1, minus lambda times the identity. So I have a minus lambda here, and the minus lambda here. I have to calculate this determinant. This determinant is easy because it's 1 minus lambda times minus 1 minus lambda minus 1/2 times minus 3/2. And this gives me lambda squared minus 1 given by this plus 3 over 4 given by this. And this is equal to lambda squared minus 1 over 4. This thing here, in order to find the eigenvalues, this must be equal to 0. So the eigenvalues of capital A are lambda equal to 1/2 and lambda equal to minus 1/2. Now, what we have to do is to calculate the eigenvectors corresponding to the eigenvalues lambda 1 and lambda 2. How do we calculate the eigenvectors? Well, we have to, what we have to do is to solve the equation A minus lambda 1 identity times C equal to 0. And A minus lambda 2 identity times C equal to 0. This would give me the eigenvectors corresponding to lambda 1 and lambda 2. So from the first one, what I get is A is 1, 1/2 minus 3/2, which is appeared here, and I'm starting to suspect that somebody is like changing these things remotely. And then what I have to do, sorry, not lambda here. Here there is no lambda. Then what I have to do is to subtract lambda 1 times identity. So here it's minus 1/2 and here it's minus 1/2. This should multiply C, so with two components, C1, C2 equal to 0, 0. If I simplify things, I get here 1/2, 1/2, minus 3/2, minus 3/2, C1, C2 equal to 0, 0. So this is equivalent to the system 1/2, so product row by column, 1/2 C1 plus 1/2 C2 equal to 0. So this row times this column equal to 0. And minus 3/2 C1 minus 3/2 C2 equal to 0. Now, the interesting thing is that basically the second line is linearly dependent from the first one. So the second line is just the first one multiplied by minus 3, which basically means that it does not give me anything new. The only one that I need is the first one. And the first one tells me that C1 is equal to minus C2. One is equal to minus C2. But there is another mistake here. So what does it mean that C1 is equal to minus C2? This means that an eigenvector of the problem is given by 1 minus 1. So I can choose C1 to be some number. For simplicity, I can choose C1 to be equal to 1, and C2 is going to be equal to minus C1, so minus 1. This is an eigenvector. What happens for the other eigenvalues? So we have to solve this other equation here. In this case, I have the matrix A doesn't change, is 1 minus, no, 1/2, minus 3/2 and minus 1. And then I have to subtract lambda 2 identity. Lambda 2 is minus 1/2, so this is plus 1/2 plus 1/2. Which multiplies C tilde 1, C tilde 2 equal to 0, 0. So this is 3/2, 1/2, minus 3/2, minus 1/2. C tilde 1, C tilde 2 equal to 0, 0. This is again the case in which the second line, the second row, is proportional to the first one multiplied by minus 1. So basically the solution of this one is given, the solution of this equation is given by 3/2 C tilde 1 plus 1/2 C tilde 2 equal to 0. The second equation is the same. And this gives C tilde 2 equals to minus 3 C tilde 1. So the other eigenvector, the eigenvector corresponding to lambda 2 equal to minus 1/2, is C tilde, which has components 1 and minus 3. Instead, in this case, was C corresponding to lambda 1 equal to 1/2. Now, what I can do is to use so basically we are trying to solve the Fredholm equation related to this kernel. Was some ux equal 1 over lambda minus f plus the sum over j that goes from 1 to n of alpha jx cj. In our case, f is equal to 0. We can assume, let's suppose that we are considering the problem in which f is equal to 0. So let me forget about this this part. Then what I will have? What are the kind of solutions that I can find? The first solution, u1 with x, is the one which is the one corresponding to lambda 1. So this would be 1 over lambda 1, which is 1/2, times C1 alpha 1 plus C2 alpha 2. So this is 1 over 1/2 is 2 that multiplies C1, what's the C1? Is 1 times alpha 1, which is 1. And then I have C2, which is minus 1, which multiplies alpha 2, which is minus 3x. I don't remember. I think it was minus 3x. So this gives me 2 that multiplies 1 plus 3x. And this is the first solution. Second solution, u2 of x is given by 1 over lambda 2. Lambda 2 is minus 1 alpha. That multiplies C tilde 1 alpha 1 plus C tilde 2 alpha 2. So this thing gives me minus 2. Then C tilde 1 is 1, which multiplies alpha 1, which is 1. C tilde 2 is minus 3, that multiplies alpha 2, which is minus 3x. So this is minus 2, 1, plus 9x. Full stop. It's completely wrong here. There is a mistake. Mistake. Where is the mistake? Yes, because actually it's this one. So basically this means that the matrix is this one. So the method is the same. The kind of calculation is really the same. Don't touch anything. It's better if you don't touch anything. And if you know, so in my notes there is the correct calculation. Okay, the method that we have described is correct. Actually, there is this mistake at the beginning here in the definition of the element of the matrix A, because actually this should be this inner product, and this is important because basically this change the matrix in this way, and then you have to do the calculation exactly in the same way. You will find some similar result. I'm sorry, there was just this. There is this typo in my notes that confused me. In any case, you will find the correct calculation with the correct numbers of my notes. The method is okay. The method that we have described is okay. I think it's useless now to spend other 20 minutes to correct this mistake, which is just algebra.
Non vengono al contrario inversi.
Infatti viene
Prof?
Sì.
I don't understand. What is the mistake?
Yeah, the mistake was here. Just here. So basically what I wrote here before is integral between 0 and 1 of alpha I x beta j x in the x. So the elements of the matrix that I was finding were the transposed of the matrix that I have to have, because instead this should be the integral between 0 and 1 of alpha j beta I. So basically what happens is that the element 1, 2 that we found should be the element 2, 1. And the element 2, 1 that we found should be the element 1, 2. And so the correct matrix is this one, not the one that we wrote. And this is changing the results of the eigenvalues are the same, because transpose has the same eigenvalues of the original matrix, but the eigenvectors are different. Indeed, the eigenvectors that I have are this one should be 3, 1, and this other one should be 1, 1. And this is changing also the solution here.
Okay, understand. Thank you.
But guys, the method is going to be algebraic. I mean, using the matrix that we wrote, this is correct. Unfortunately, the matrix that we wrote, that I wrote, is wrong. And the rest is wrong. But again, you can find on my notes the correct result. Let's do a break.
Dalla matrice che avevo scritto in poi il calcolo giusto.
Dalla matrice in poi il calcolo è giusto, va bene. Il problema qual è? Che poi il risultato che trovi alla fine è sbagliato. Se cambi la matrice e metti come matrice questa qua che ho messo, la trasposta di quello che sta scritto là, trovi il risultato giusto, che è quello che sta poi dopo sulle note. Il problema qual è? Che nelle note, come un minchione, ho scritto gli elementi di matrice come l'abbiamo calcolata a lezione, e poi però la matrice l'ho scritta bene perché mi sono fatto il calcolo da un'altra parte. E ricopiando questo qua adesso a lezione non ci ho fatto caso, pensavo di aver sbagliato la matrice.
Prima calcolo un dubbio mentre scriveva.
E ci ho avuto un dubbio perché quando ho calcolato l'elemento 1, 2 non era l'elemento 1, 2 che avevo qui, però pensavo di aver fatto io un errore quando ho fatto il calcolo. Adesso ho detto vabbè, tanto è un calcolo algebrico, te lo posso fare pure al momento senza problemi perché si fa, è semplice. Il problema è che alla fine invece avevo ragione qua. Vabbè.
No, ma fare un esercizio.
Sorry, Professor.
Yeah, tell me.
How can we find a function is separable? For example, in the last example, you wrote alpha 1 equal to 1. I didn't understand.
Yeah. Well, actually, you have to try if it's possible to separate the variables. So the idea is that you should be able to split the kernel in pieces which are products of only one function. That's actually why I was doing the example of the square root of x plus y, because the square root of x plus y, well, cannot be separated in this way. You have to check actually case by case. The case that we have studied, this one, I can write this thing. Yeah, this thing can be written as a first term that is 1 and the second term which is minus 3xy. Correct?
Yeah.
1 can be expressed as the product of two functions which are one function of x and one function of y, which are 1 and 1. Because even if they are constant, they can be, I can say that this is a function of x and this is a function of y, in which the functions are just constant. And this other one can be written as the product of a function minus 3x times a function y. You can eventually do also another split. You can write this as 3x and minus y. This is something that you can do. Or you can write this as x or minus 3y. This is another thing that you can do because x times minus 3y is minus 3xy. But you have to check time by time if you can separate in this way. There is no recipe for separating the kernel.
It depends on us how we separate this. It's not a unique solution for separate the coefficients. I mean, you wrote in different ways.
If I wrote in a different way, I should arrive to the same solution. Still, I should arrive to the same solution. Up to constant factors.
Yeah. Thank you.
So I arrive to independent solutions which linearly depend from the solutions of the case that we have calculated. This is better said. So the idea is that I'm finding independent solution for any independent eigenvalue. The independent solutions that I'm going to find are linearly dependent from the solutions that I have found in this problem. So this is it's not a problem how to separate the kernel. The problem is to find, as you correctly are saying, the problem is to find an expression for this separation of the variables, and sometimes it's not trivial. So another case, I guess that's this one, y to the power x. It's again something that you cannot separate in a sum of products of functions just of y and x. Che è successo? Problemi? No, sta a posto.
È stata una settimana lunga.
Non ho capito?
Siamo stanchi, è stata una settimana lunga.
A proposito, ma lunedì è festa?
Sì.
Ok.
In vacanza?
No, i morti è il 2.
No, è due.
I santi. Il lunes è santo, il 2 è morto.
Vai in santi. In festa da domani fino a martedì.
Ma martedì compreso.
No, martedì siamo...
Martedì si fa lezione.
Sì.
20 anni fa era festa.
Ho fatto la scuola cattolica e la festa. La scuola del mondo.
Che poi nessuno andava al cimitero, ma stava al cimitero il 2 novembre, mai. Per un anno mi sono fatto un po' più di una mesata in Messico e là è tosta la cosa.
È festa.
È festa, ma proprio festa.
Sì,
La Santa Muerte. La Santa Muerte. E si devastano. Mi sono devastato pure io. Vuoi dire. E adesso è un po' complicato. Adesso hanno parecchi problemi. È tutta merda di narcotraffico.
Allora, è stato però un trafficante.
Questa settimana in Colombia. Però in Messico in questo momento fra i problemi che hanno per questa cosa dei narcotrafficanti in tutto quanto il paese, e il Messico è un continente gigantesco. Il problema che hanno al confine della gente che sta cercando di andare negli Stati Uniti, lì li tufano di mazzate, ma proprio malamente. Su questo c'è stata una svalutazione del peso impressionante per mezzo del Covid, però quello l'hanno subito tutti quanti i paesi. Il Brasile sta ancora peggio.
Il
Brasile stanno rovinatissimi anche perché c'è un presidente che te lo consiglio. Tra l'altro ieri al presidente del Brasile, che si chiama Bolsonaro, gli hanno dato la cittadinanza onoraria di non so che paese qui in Italia, ed è insorta, la gente del paese è insorta perché diamine, cioè in questo momento storico metti a dare pure la cittadinanza onoraria a Bolsonaro, che è l'ultimo personaggio a cui ti vuoi collegare, perché sta veramente, cioè, stanno sull'orlo di una crisi di governo, cioè hanno paura di colpi di Stato, cioè stiamo parlando proprio di... sono terrorizzati dal fatto che questo si alza la mattina e fa colpo di Stato. C'è un botto di amici brasiliani che sono veramente terrorizzati. E non faccio nome perché siamo registrati, perché altrimenti mi metto pure guai. Però... terribile la situazione. Vabbè, dai, ultima trama. Cominciamo. So, we are not able to complete the discussion on the Green's function, and I'm happy because then this would be completed on the 2nd November. There is just one tradition that doing on 2nd November. Listen to Totò, because there is a famous poem by Totò on 2nd November, which is La Livella. Okay, let's consider the Sturm-Liouville problem, and I will write in operator notation given by the following. So the operator A gives me basically minus P U prime plus Q U. Equal to F. Okay, this is I don't like it. Let's write it correctly. So AU equal to F, where AU of X is equal to minus PU prime plus QU. Q and P are nice functions. So are functions which are continuous, well defined in the interval AB, and so forth and so on. And then I have generalized boundary conditions that I will write as B1 UA equal to 0 and B2 UB equal to 0. These are also defined in operator notation. So basically this means that B1 UA is defined to be alpha 1 U of A plus alpha 2 U prime of A, and B2 UB is defined as beta 1 UB plus beta 2 U prime in B. So basically this is a condensed way to rewrite the boundary conditions, right? Because this basically would mean that alpha 1 UA plus alpha 2 U prime A is equal to 0, and B1 UB plus, beta 1 UB plus beta 2 U prime B equal to 0. What we have called yesterday generalized boundary conditions. The funny thing is that usually what you find, and what you will find also in the book by Logan, you can condense even more the notation. So you can write this thing in just one line in this way. So basically this operator, this is an operator L which acts on U equal to F. This is an equation in the operator notation that includes, number one, the differential equations in per set, so the first line, AU equal to F, and then it's supposed to include also the boundary conditions. So you can imagine this as if L would be A, B1, B2, and if this new U is U, A, UB, and then this new F is F0 and 0. I mean, you can think about this. Of course, this is not very precise, because then well, of course, I cannot consider this as the scalar product, because otherwise I would have some of these terms, which I don't want. So what I'm saying is that you can think about this equation as A applied to U equal to F, B1 applied to UA equal to 0, B2 applied to UB equal to 0. Okay, that's why I'm condensing in this way. Why I'm doing this? I'm doing this for a simple reason, because I want to because I want to write, I want to invert the this equation to write the solution U of my problem as the inverse of the operator L applied to F. Again, in this inverse of the operator L, I am also considering the boundary conditions. That's everything, including in capital L. Back to the case of a matrix. If I have this thing, in order to multiply for the inverse, so I want to find x, I can find x as a minus 1 c, right? I'm multiplying by a minus 1 on the left. What's the condition that I have for having the inverse of a matrix? When is it possible to write a minus 1? Do you remember? Yeah, actually, a minus 1, a equal to identity is a consequence, but when that's actually not enough. Yes, exactly. So a matrix is invertible if it has a determinant which is not 0. If the determinant is 0, I cannot define the inverse of the matrix. So right. Now, let me give an ansatz for this object. Now, I want to think about the operator L minus 1 as an integral operator, as the integral operator k kappa, which we have used in previous problems. Okay. So let me do this ansatz. I say that L minus 1 is acting on the function f as the integral of the interval AB of some function g of x c f c dx. So basically I'm saying that L minus 1 is some integral operator with a kernel which is given by g of x and c. Now, if this object exists, this function here is what would be called the Green's function associated with the operator L. And what I would like to prove is that this green function exists for the stimuli problem and is defined by the following formula: g dx and c is equal to what? To minus u1x u2c divided by pcwc minus y, this is for x less than c, y u1 c u2 x p of c w of c x larger than c, where U1 and U2 are independent solutions of the homogeneous equation, the associated homogeneous equation. AU equal to 0, with the boundary condition given by B1 U1A equal to 0 and B2 U2A equal to 0. So basically U1 and U2 solve the homogeneous differential equation, but with one with the boundary condition B1 and the other with the boundary condition B2. Not clear. So in order to find the two equations, the two functions, U1 and U2, I have to solve the problem AU equal to 0, B1 U1A equal to 0, and this is giving me U1. And then I solve AU2 equal to 0, B2 U2B equal to 0, and then this gives me B2, U2. What's P? This function P is the function that is in the operator A, is this function here. What's W? W is the Wronskian. You remember what's the Wronskian? No. U1 of x derivative with respect to x of U2 minus derivative of 1 with respect to x times U2. Wronskiano da W-R-O-N-S-K-I-A-N. Finalmente è scritto una chiave. What's this thing, guys? Have you ever seen this function? Have you ever seen this function? The theta function, step function, a function which is 0 when x is less than 0 and 1 when x is larger than 0.
Oh, yes.
So basically this is a function which do like this. So for x less than 0 is 0, for x larger than 0 is equal to 1. So this theta is a generalization of the other. Guess how does it work, in your opinion?
X is smaller than
Xi. And if x is larger than Xi, that's actually how does it work. And why I want this? Because I can condensate this expression, the expression for the Green's function, can be rewritten in terms of the theta function in this way. I can write g of x and c as minus 1 over p of c times the Wronskian of c times the theta of x minus c u1 c u2 x plus the theta of c minus x u1 x u2 c. Well, just a way to write in a short, it's not even so short, in just one line, the entire solution, the entire expression for the Green's function. Now, what we want to do is to prove that this integral which this thing here. Want to prove that this integral is a solution of the Sturm-Liouville problem. So we want to prove that this thing plus boundary conditions are fulfilled. You see, if I'm able to prove this thing here, this means that capital I is the solution of this thing here. Okay? So I'm writing capital I. Questa cosa green fumato. Vabbè. Yeah, so then capital I is, this would prove that capital I written in this way, so as the function which I obtain as the integral of the Green's function times f is a solution of the Sturm-Liouville problem. BCS is boundary conditions. Yeah, sorry, it's the way I write boundary conditions. Parentheses, many times I'm writing in my notes this, which for me means with respect to. Which is not this. Okay, let's write the integral I. I always say that it's the integral between a and b g x c f of c del c. Let me use the expression that I have of the Green's function. So you have the integral between a and b. Let me use the first p's. So I have minus 1 over p w theta of x minus c u1 of c u2 of x times f of c d c. vabbè, scriviamolo tutto. Quindi, and then I have the second part, which is the integral between a and b of -1 over pw, theta of c minus x, u1, u2, f xc. 1 of x, u2 of c, f of c, xc. Now, remember that remember that this object, theta of x minus c, is equal to 0 when x is less than c, and is equal to 1 when x is larger than c, right? So the only part of this integral that I'm interested in is when c is smaller than x. If c is larger than x, this object is 0, right? This is 1, this is 0, right? So this means that instead of calculating the integral between a and b, I can calculate the integral between a and x. The integral, remember, the integral is in c, right? So this thing here means that I'm considering c between a and b. But instead of considering c between a and b, I can consider c between a and x. Because if c is on top of x, this function is 0. So does not contribute to the integral. The only part that contributes to the integral is up to x. Such a way that I can write this object here as the integral between a and x, the minus is in front, 1 over p of c w of c, u1 of c, u2 of x, f of c, dx. E l'altro al contrario. L'altro sarà, the other one will be, well, there is a minus sign also here, the integral between x and b of 1 over p of c, w of c, u1 of x, u2 of c, f of c, dx. In this way, again, first of all, write an easier, a shorter integral. I can get rid of the theta because basically I have already taken into account the theta, stopping the integral to x here, or starting the integral from x here. And for this reason, I didn't write the theta. The theta is basically inside the fact that now these extremes are different. We have to use again the Leibniz rule. So the Leibniz rule will let me write again the index of the integral between ax and bx. Come on, but I cannot, non posso combattere con queste cose che scompaiono. X, y, dy equal to the integral of between ax and bx of the partial derivative of f with respect to x plus f the of x b of x, the derivative of b with respect to x, minus f of x a x, derivative of a with respect to x. So what we have to do is we will have to use the Leibniz Rule. Why? Because we have to calculate, and this is what is gonna be a bit longer. We have to not calculate, but to verify that AI is equal to F. What's A? A is minus P I prime plus Q I. This must be equal to F. So what I have to do is to calculate the derivative, the first derivative of I, and then to calculate the derivative of all these things, and then to verify that this is correctly defined. All right, let's start with calculating the first derivative of I. What's the first derivative of I? The first derivative of I is given by, let's start from the first term. So what I get is minus integral between a and x, 1 over p w, u1 of c, f of c. The only function which depends on x is u2. So this is a derivative of u2 with respect to x. And then I have to add this term here, which is the function evaluated in the upper limit, which is x, times the derivative of x with respect to x. So what's the function evaluated in x? Is here there is a minus sign, 1 over p of x, w of x, u1 of x, u2 of x, f of x, times the derivative of x with respect to x, which is 1. And then there is the last term, which is f evaluated in the lower limit times the derivative of the lower limit of the integral, the lower extreme of the integral, derived with respect to x. But the integral is between a and x. A does not depend on x. So the derivative of a with respect to x is 0. So this term does not contribute. And this completes the first term. Now we have to calculate the derivative of the second term. The derivative of the second term has a first part, which is integral between x and b, 1 over p w. The only function which depends on x is u1. So this is a derivative with respect to x of u1 times u2 f the c. Then I have to calculate using the Leibniz Rule. I have to calculate this part here. But in this case, the upper extreme of the integral is b, which is constant, does not depend on x. So this part is 0. In this case, the only part that I have is this. And with b, then minus, there is a minus sign here in front, so it's a plus f evaluated in the lower limit, which is 1 over p of x, w of x, u1 of x, u2 of x, f of x, times the derivative of the lower limit, which is x, with respect to x. The x in x in the x, the x in the x is equal to 1. Full stop. This is the first derivative of I. This term and this term cancel each other because they are the same. Vabbè. Adesso, let's put these things that we have found into our equation here. So I have yes, minus p that multiplies all these things, so minus integral ax 1 over p w u1 f u2x, let me write it this way. And then I have minus integral between x and b of 1 over p w u1x u2f. This is I prime. And then all these things I have to calculate the derivative plus qi equal to f. Now I have the derivative of p. So since this is the derivative of a product, I have to do the derivative of the first times the second plus the first times the derivative of the second, right? So I have minus sign in front of everything. Then I have p prime times all this thing that is here. And then I have p times the derivative of what is here in parentheses. So we have to do another time the Leibniz, we have to use another time the Leibniz rule. If I use another time the Leibniz rule, what I found is minus integral between a and x 1 over p w u1 f u2 x x. And then I have minus 1 over p of x w of x u1 of x u2x of x f of x. And now I have the derivative of the second piece, which is minus x b 1 over p w u1 x x u2 f. And then I have qui plus u1 x of x u2 of x f of x divided by p of x w of x. Then outside I have qi, which is the one that I have here, equal to f. We have almost done, guys. Now, what I have to do is to use the fact that U1 and U2 are supposed to be solutions of the associated homogeneous with the two different boundary conditions. The things that we have written here. If I'm using this, what does this mean? So basically this means that A U1, this is minus P U1 prime plus Q U1, this is equal to 0 with B1 U1 B1 U1 A equal to 0. And then I have A U2, which is minus P U2 prime plus Q U2 equal to 0 with B2 U2 B equal to 0. If you use this condition, what you find is this. This term, what is the other one? This term, and this term all cancel out because of these conditions. Then actually correct. We can do explicit calculation, but this would be very long. And I do not want to stay here.
Also QI.
Also the QI here inside, because you have the Q1 and QU2 here, which is basically allows you to kill also this part. So what will survive is this part plus this part. There is a minus P here in front equal to F. So what survives is minus P that multiplies minus U1 U2 X F divided by PW plus U1 X U2 F divided by PW equal to F. This P simplifies with this piece. There is a minus sign here in front. This combination, minus U1 U2X plus U1X U2 is minus the Wronskian. So this is minus Wronskian F equal to F. Magic. So basically this allows us to prove that this solution written as the integral between a and b of a kernel which we define to be the Green's function g of x and c times f c x c is a solution of the Sturmeville problem that is defined in here. And today I will stop here because there is a lot of material and a lot of calculations. Yeah. Any question?
Nothing.
Mi piace. Va bene, guys. Then at home, I can see that there are a lot of foreigners, and probably you don't know. We were discussing before. On 1st of November, it's holiday. So we will not have a lecture next Monday, but we will have a lecture on Tuesday. Okay?
Okay.
Right.
Okay,
Good
Professor.
holidays.
All right, Professor.
Bye bye.
Andy, tu lo sai. Che dici? Sei l'unico che probabilmente lo sa.
Va bene, prof. Saluti.
Ciao.
Lezione, Andy.
Cheers, guys.
Thank you, Professor.
Bye.